So, good evening, friends. Myself, Fathima Shijad. I am a third year electrical and electronics engineering student at TKM College of Engineering. So, my topic is DC to DC converters, which is a much simple topic. So, let us begin. This is just an overview of our session. So, what is DC to DC converters? DC to DC converters are an integral part of our modern life. They have many applications in the modern world. They actually provide the required power to the communication backbones. They are used in digital devices, cell phones, and they have widespread applications in electric cars. So, so DC to DC converter is actually a small topic from power electronics. As you all know that power electronics is the application of solid state electronics for the control and conversion of electric power. So in power electronics, we can divide the converters into four groups. First one is AC to DC converters, which we usually call as rectifiers. The second is DC to AC converters, which we usually call as inverters. And the third is DC to DC converter. And the fourth is AC to AC converter. So today we are going to concentrate on DC to DC converters. DC to DC converters convert a voltage level to another with high efficiency. So now let us move into the anatomy of power electronic converters. So every power electronic converters consist of four main components which I have listed. The first one is the energy source. The second is the power circuit. Third, control circuit. And fourth, the load. So all of you might know that energy source provides energy to the load. So it is the function of energy source. Now, in most of the cases, there will be an intermediate block power circuit between energy source and load. Because sometimes it is not possible to connect the energy source directly to the load. So let us take an example. If the energy source is a DC source and the load is an AC motor, then you need definitely to convert DC to AC, right? So the power circuit in that case will be an inverter. Similarly, if input energy source will be a low voltage DC and you want high voltage DC at your load, then you will substitute a corresponding power circuit over there. So power circuit is composed of switches, inductors, and capacitors. It does the conversion of energy, so the output is in the form required by the load. Now, the third component, that is the load. I don't want to explain much about load because we all know that load is usually a machinery designed to accomplish a specific task. So the fourth component is actually known as the brain of the system, that is the control circuit. So why is it called so? Since it provides the required signal to the power circuit, that's why it is known as the brain of the system. Actually, control circuit can be divided into two broad categories. The first one is closed loop control and the second one is open loop control. So you can see in this open loop control, there is no arrow connecting the load and control circuit. While in your closed loop control, there is an arrow connecting control circuit and load. So which means that in closed loop control, it uses some form of feedback. That is, it senses either load voltage or current and produces the control signal based on that measurement. While in open loop control, we do not use any feedback. That is, there is no sensor to sense the load voltage. So, yeah, the designer in open loop system, the designer sets the control circuit based on some nominal values and he hopes that the output is what required by the load. If the operating condition changes, output may not be what is required by the load. So let's just take an example to understand it. Assume that we want to design a portable cell cell phone charger. So the designer may assume that the car battery has an average voltage of 12 volt, and he set solar based on 12 volt input. The user may use the charger in trucks or buses, which usually have 24 volt electricity system. In this case, the charge provides an output voltage that is around 2 times what is required. No mechanism to inform controls in this output. Needlessly, converters which use closed system will be more accurate and will be more load control. Now we can move deep into DC to DC converters since that is our topic, right? So here I am introducing switch DC converter. So let us examine what it is. Here I have explained it through an example to understand it in a much better way. So here I have assumed that a 1 ohm load, 1 ohm resistor is connected as a load with a 9 volt battery. But I only 3 volt in the load side. So I want to decrease the input, or I want something which consumes 6 volt so that the rest 3 volt will be available as the output. Right. So here I am connecting a 2 ohm resistor in series with the load. So the load voltage will be 3 volt. I have explained further. Let's check it. So we know that by Ohm's law is equal to IR. So I is equal to V by R. So actually, current through the circuit is 9 divided by the sum of the resistance, since it is current in series, right? So it will be 3 ampere. And the voltage across the 2 ohm resistor will be is equal to I into R, that is 6 volt. So 6 volt is being 6 volt is there at the 2 ohm resistor. So naturally 9 minus 6, 3 volt will be there at our load. So our need is satisfied. So now,
Excuse me, Fatima.
but let us calculate the efficiency of the above circuit, right? I have already mentioned, right? So the efficiency, as you might know, that efficiency is the output power divided by the input power. So from the above calculations, we know that current I is equal to 3 ampere. I have already mentioned this slide.
Sorry for that. We are experiencing some network issues. I request everyone to stay patient. We'll be back in a couple of minutes.
I'm sorry, my network has got interrupted. So let us continue. Is it audible, right?
Yes, you are audible.
Okay. Okay. So this was a circuit. Now I am going to calculate the efficiency of this circuit. You know that efficiency is output power divided by input power. So from the above calculations, we have obtained that the current is 3 ampere. Right? We have obtained it over here. So your output power will be I squared R, that is equal to 3 squared into 1, it's about 9 watts. And your input power will be V into I, that is 9 into 3, about 27 watts. So the efficiency will be 9 divided by 27, that is about 0.333, that is 33.3%. So by using a resistive divider, we only get 33.3% of efficiency. So we need to move into another circuit so that the efficiency is increased. So here I have replaced the resistor by a transistor. You can see it over here, right? So this is a transistor. The rest things are same, that the input voltage will be 9 and the load resistor will be 1 ohm. So here the Zener voltage is about 3.7 volt and the base emitter voltage is about 0.7 volt. And your output voltage will be Vz minus VBE, right? So it will be 3.7 minus 0.7, that is approximately, that is equal to 3 volt. So we know that 9 volt was the input voltage. So naturally the VCE, that is collector emitter voltage, will be 6 volt. That is actually the voltage across this, right? So, and you can also say that the current through the transistor is same as the current through the load, right? You can see that. So we have already calculated the current flowing through the load, that is approximately 3 ampere. So the transistor dissipates around 6 into 3, that is 18 watts. 18 watts of power is being dissipated by the transistor, which is same as that of a resistor, right? So here also we only obtain 33% efficiency. So the efficiency is not increased. So let us move into another circuit. So here I have explained the basic, I am going to explain about the basic idea of a switching converter. So, okay. Yeah, here I have replaced the transistor by a switch. I will show it. Yeah. So when the switch is in position 1, it is considered as on position of switch, and when switch is in position 2, it will be considered as off position of the switch. So what happens here? Let us check it. So when the switch is in position 1, that is the equivalent circuit of position 1 is shown here. That is, it is approximately a short circuit, right? So when the switch is in position 1, it will be a short circuit, and when the switch is in position 2, it will be an open circuit. So here I have considered the switch to be ideal. Okay, that is, there is no losses. So when we place the key in position 1, the output voltage will be 9 volt, right? The input voltage will be same as that of the output voltage. And when the switch is in position 2, the output voltage will be 0 volt. So when the switch is in position 1, the current will be 9 ampere. By Ohm's law, we can obtain it as 9 ampere. Since the switch resistance is assumed to be 0, the power dissipated by the switch will be I into R square, that is 0 into 9 square. So naturally it will be 0 volt, since I have considered the switch as an ideal switch. When the switch is in position 2, no current passes through the switch. So we can say that in that case also the dissipated power by the switch will be 0 volts. So what I am trying to convey is that the efficiency of this circuit will be 100%. That is, when I have introduced a resistor or transistor, the efficiency was only 33.3%. But when I have introduced an ideal switch, it will be 100%. In reality, there is no ideal switch, right? The switch will be real. So there is some form of dissipated power. Despite these dissipation, the efficiency is high enough, right? Since in the previous cases, we have obtained only 33%. So by using switch, we can obtain maximum efficiency. So what you can conclude is that by using switch mode converters, the efficiency will be very high. Okay. Now let us move on to next slide. Hello, am I audible?
Yes, you are audible.
So let us compare a linear laboratory power supply and a laptop adapter. So in linear laboratory power supply, there will not be any switch mode, but in laptop adapter, we use a switch mode system. What I'm conveying is that the weight of the linear laboratory power supply is 9 kilogram, and that of a laptop adapter is about 400 gram. But the output power, it is about 90 watt in both cases, right? And the efficiency is also different. The efficiency is very low in a linear laboratory power supply, and it is about 85% in laptop adapter. So although the output powers are the same, the weights and volumes are not, right? So generally the switching converter are more smaller and compact than their linear versions. That is an advantage of switch mode converters. Okay. So in the next two slides, I'm going to give a brief idea about two basic DC to DC converters. The first one is buck converter. Okay, buck converter reduces the input voltage level. That is, the output voltage will be less than the input voltage. Let us examine it. For examining this circuit, I have used an equation called volt-second balance equation. I'm using volt-second balance equation because in switch mode power conversion circuit, we use this equation. Volt-second balance refers to the fact that over one complete switching cycle, the total volt seconds applied to an inductor must be 0. We can actually prove it mathematically, but I'm not going much deeper. So that is your on voltage of inductor into your on time plus off voltage of inductor into off time will be 0. So let us apply that equation to the circuit. The on voltage will be Vi minus Vo, right? It will be when the switch is on. That is the on position. So the voltage across inductor will be Vi minus Vo, and the on let the on time be T on. So Vi minus Vo into T on plus off voltage, that is off voltage across inductor. Since it will be an open circuit, so Vi will not be there, so it will be minus Vo into off time, that is T off. So Vi minus Vo into T on minus Vo into T off equal to 0 will be your volt-second balance equation. On solving, you will get Vo is equal to D into Vi. D is known as the duty cycle of the buck converter, that is T on by T. So when solving, you will arrive at this equation. Okay. So I have mentioned that duty cycle is T on divided by T. T on is smaller than T. So naturally, D will be always less than 1. Or what you can convey is that VO is equal to D into VI. So naturally, VO will be less than VI. It is a buck converter. Neglecting the power losses. If the losses are 0, you can equate that P in is equal to P out. That is V in into I in is equal to V out into I out. Or by rearranging, you will get this equation. I have written it equal to D because VO by VI will be equal to D from this equation, right? So it will be V out by V in equal to I in by I out. So this equation will be familiar to most of you, that yeah, it is somewhat similar to your transformer equation. That is V2 by V1 is equal to I1 by I2. If you are substituting V out is equal to V2 and your V in is equal to V1, and correspondingly for the current parameters, you will get the same equation as a transformer. So buck converter is actually known as a DC to DC step down transformer. That point is very important. That yeah, it is very important that I will tell you in later. Now let us move on to the next converter, that is known as boost converter. As the name suggests, it's boosting up the voltage. That is, the output voltage will be greater than input voltage. In a similar manner, we can apply the volt second balance to this equation, this circuit also. So you will arrive at this equation. VO is equal to VI divided by 1 minus D, where D is T on by T itself. But it is VI divided by 1 minus D, right? So naturally, VO will be greater than VI, or you can say that it is a boost converter. In this case also, we are neglecting the power losses, or the losses are assumed to be 0. So P in is equal to P out, that is V in into I in is equal to V out into I out, and you will arrive at, by rearranging, you will arrive at this, that is V out by V in equal I in by I out equal 1 by 1 minus T. So in this case also, you can see that V out by V in is equal to I in by I out. It is somewhat similar to your transformer equation. So what you can conclude is that your boost converter acts like a DC to DC step up transformer. Okay. Hope these things are clear to you. So now we have a brief idea about DC to DC converters, like two basic DC to DC converters. What is a buck converter and what is a boost converter? Hope it's clear. So now I'm diverting something to the historical part of our electric power transmission. So let us examine that part. During the early days, the scientist, the very famous scientist Thomas Alva Edison, suggested that suggested a DC power transmission system. But DC was not able to transmit over long distance. So at that time, George Westington, another scientist, suggested an electric power transmission system using AC source. Since AC can be transmitted over long distances, the thought suggested by Edison was discarded, and the thought suggested by Westington was accepted by the world. But by taking losses into account, AC transmission has much power loss than DC. So why we accepted a transmission system suggested by Westington at that time was due to transformers. In those days, power converters were not much developed. We do not have any DC equivalent transformers for DC power transmission. But now the things are really different. Now we have more developed converters. I have said that we have step down transformer, DC equivalent step down transformer, and step up transformer. That is, we have buck and boost. So also the high voltage DC links are being developed. So in future, maybe things will change, and we can hope that AC power transmission will be replaced by DC. I have mentioned this fact that to make you aware that DC to DC converters and that to buck and boost are of utmost importance. So that's why I have mentioned it. So that's it. So now we are moving on to the about the last session of the last topic of the session, that is applications of DC to DC converters. I have only mentioned 2 applications which is used in our daily life. I haven't mentioned all those, but there are many applications for DC to DC converters. I have chosen these 2 because it will be more familiar to you. That's why. Okay. The first one is solar panel. We know that by using solar panels, we will get a voltage, right? The voltage will be a low voltage. So if we want a higher voltage, we can introduce a boost converter. So this is an application of a boost converter. So if you are introducing a boost converter, you can actually get your higher voltage if you want to. And the next application is charging of batteries. Similarly, the second application is charging batteries. That is the figure shown here as a step-down converter, which we usually use in cars, right? You people might be familiar with this thing. While traveling, we always use this. The car battery provides about 12 volt while charging, but the phone battery needs only 5 volt. So in such a case, we can use a step-down converter, that is your buck converter. So these are some of the applications. So in this case, we have used a buck converter, and in this case, we have used a boost converter. There are many more DC to DC converters are there, like buck boost converters, chook converters, and many DC to DC converters are here. And there are many applications for that. Okay, so that was the end of the session. Hope you have understood what I meant. Okay, thank you everyone for attending the session, and thank you for listening me. I also thank IEEE for giving me such a chance to be a part of the Power Talks. Okay, thank you. Stay happy, stay safe, and stay healthy. Thank you.
Thank you, Fatima Shijad. It was an informative presentation. I would also like to thank all the participants for listening and participating in this 8th Power Talks by IEEE Kerala chapter. Thank you all.